Hello, everyone. Welcome to Module 3. I'm Yanting Ma from Mitsubishi Electric Research Lab. Today, I'm going to talk about physics-inspired operator learning for inverse scattering, and our motivating application is ground-penetrating radar. This is joint work with Qingqing Zhao, who is a PhD student at Stanford, and she did this work with us while she was an intern at MERL. And also, other collaborators include my colleagues at MERL, Petros, Saleh, and Hassan. So for those of you who might be familiar with the physics-informed neural network that pins, just know that this is not pins. So we are actually using the Fourier Neural Operator architecture, and we modify the architecture based on our understanding of the physics of this problem. So this is not the pins. Okay, let's get started. First, let's see what is this ground penetrating radar and how the inverse scattering is involved in this application. The ground penetrating radar is a non-destructive way for underground mapping. For example, if I want to see the structure of our the structure of the underground, say the layered structure of the soil, or like if there is a pipe in the buried in the ground, but we don't want to dig a hole in order to find where the pipe is. So we use this ground penetrating radar. Is like this. Let me change to the printer. So we will have a card where there is a box on it, and in this box is the ground penetrating radar, which consists of a transmitter antenna and a receiver antenna. So the transmitter antenna will emit electromagnetic wave into the ground, and then the electromagnetic wave will interact with the whatever structure that is under the ground, and then there will be wave reflected back into the receiver, and then those received signal is our measurements that we use to reconstruct the scene under the ground. So this different color actually represents different materials, and in the reconstruction, that appears as the electric permittivity value. So different electric permittivity value will correspond to a different material, so that once we reconstruct the permittivity distribution of the underground scene, we will be able to relate each portion of this scene to a certain material. That's how we do this mapping. So this person will push the cart, the person will stay at some location for a while and emit the wave and receive the wave, and then it will push the card to the to the next data collection location. So all the measurements will be collected for the reconstruction of the underground scene. This is an example that how the wave field looks like. Suppose that this is our structure, right? So these are two layers. This is the air, and this is one layer of the soil, and this is the second layer of the soil. And there are two cylinders. You can think of it as the long pipes. And then there's no video. Yeah. And then suppose we are looking at this transmitter and this receiver. This transmitter will emit electromagnetic wave into the ground, and then you can see that when the wave arrive at those intersections, essentially anywhere there is a change of the permittivity value, you will see that the wave is being reflected back into the air, and then we will receive whatever wave is being recorded at the specific sensor location. And if we consider multiple pairs of transmitter and receivers, and then arrange their the received data into this matrix. So in this matrix, each column corresponds to one pair of transmitter and receiver, and this is actually the received wave as a function of time. So if you plot a column out, you will see like a wave-like curve as a function of time. So these are our GPR data. So in this problem, the forward problem is to compute the wave field at the receiver locations given this ground truth permittivity map. And then the inverse problem, which is actually the ground penetrating radar problem, is that given the received electromagnetic waves at those sensor locations, essentially just this matrix, then we want to reconstruct this permittivity distribution under the ground. So this is the this inverse problem is the inverse scattering problem. So the physics behind this is that, so we are talking about the wave description of light. So our governing equation is the Maxwell's equation. And to make the problem simpler to describe, we will consider a 2D setup. And we also assume that all materials are non-magnetic. And then for the 2D setup, we mean that the permittivity distribution, which is originally a function of the 3D positions, X, Y, Z, but we assume that it is varying only in the XZ plane. So we consider horizontal is X, vertical is Z, and then the Y direction is into the slide. But we assume that there is no change in the Y axis, meaning that if this is a pipe, then this pipe is infinitely long compared to the wavelength that we are considering. And also this layer structure is also like extending infinitely long along the y-axis. And then we also assume it is time harmonic fields. So the time dependence is completely described by this complex exponential. And then the source is a point source in 2D, which means that it is a point in the XZ plane, but it is infinitely long along the y direction. So there is also no variation in the y direction. That's why we can just consider this as a 2D problem. So in this case, the Maxwell's equation reduced to a scalar wave equation like this. This is known as the Helmholtz equation. And then this EY, meaning the y component of the vector field, the vector electrical field. So only the y component is non-zero, and we only care about the y component. And then to simplify the notation, we will let rho denote these 2D coordinates, and we use U to denote this y component of our electrical field. And it can be shown that the solution of that differential equation satisfies this integral equation. Here, this F is called the permittivity contrast. It's essentially the difference with respect to whatever we consider as the background permittivity. And then this U in is the incident field, which depends on the source and also the background. And this G here is the Green's function, which is the fundamental solution of the differential equation, of the homogeneous differential equation, the solution for this one. And because now we reduce our Maxwell's equation to the scalar wave equation, so this integral equation is actually known as the Liebman-Schrödinger equation, and it is commonly used for solving inverse problems. So I mentioned like this background permittivity. There are actually two ways to select the background. So we can consider the free space as the background, but although we plot our permittivity map within this bounded domain, we know that in reality, the ground is actually infinitely large, right? So this layer structure actually extends horizontally to infinity. So if we consider the free space as the background, then these artificial boundaries that we created by limiting our computational domain to be within this bounded domain, then we have to consider some type of absorbing boundary conditions so that we don't have this reflection coming from this artificial boundary, because there's no boundary here because the ground is just extends to infinity. And this is not very easy to do. And That's why we use a learning-based method to solve the problem in this case. And the second choice for the background could be this layered structure. Say our background will be air and the layered structure in the soil, meaning that without these two objects, I consider that as my background. And now my background is a layered structure. And now we have to compute our incident field and also our Green's function for this layered structure. So unlike the case for free space where the Green's function has a closed form solution and it's very easy to compute, for the layered structure, for each row prime position pair, that Green's function needs to evaluate an integration to get the value for every spatial location pair. So that is very, very computationally expensive. But it is durable. So if we know or if we can estimate the background, and then we can compute the Green's function for this background, and then we can just use model-based method, like classical method, to estimate the object that is buried in this layered structure. This is totally durable, but it's very computationally expensive, and we will show an example right now. So let's first see model-based methods. I know like this is an AI workshop, but because we are not doing the inverse scattering, we're not learning a end-to-end neural network. We only replace our forward operator with a neural network in our learning-based method. And everything else, including the optimization procedure for estimating the permittivity map, is the same as what we do in our model-based method. So I think it's important to understand what we are actually learning and what is actually the more, I would say, classical or more not learning based. It's not like a black box thing for the whole procedure. So we will consider a hat space setup, but this is the easiest layered structure that we have. So we have air and soil, and we have source and the receiver. So this will be considered as our background. And then we can compute the incident field and the Green's function. And there is a formula that you can evaluate those values. And then the details will be in the textbook called Introduction to Ground Penetrating Radar, Inverse Scattering, and Data Processing. We're not going to go into the details about this because our focus is the learning-based method. So this is our background, and we can compute the Green's function for this background. And the incident field means whatever we have a source here, and whatever the field is at different locations will be the incident field without any objects in it. And then once we have the object, then we will have a total field that is being received at the receiver. And the inverse problem would be how to reconstruct this object using the data that we collected at the receiver. And notice that because now we are considering the background as this infinitely large layered structure, the non-zero part in our permittivity contrast, which is defined in this way, this will be zero outside our computational domain. So suppose this is the only object in the soil, right? And we restrict our computational domain to be just slightly larger than where my objects are. And then everything outside my computational domain will be zero in the permittivity contrast. That's why when we evaluate this integration, originally this has to be over all R2. And because F will be zero outside omega, we can just limit the limits for the integration to be omega. And in this way, we can now discretize this integration. Suppose that we discretize our computational domain into endpoints. And our sensor position, we'll call this sigma, is our sensor positions. Suppose that we have endpoints where we put a sensor to record our data, and then we can discretize this integral equation. First, we consider rho in the sensor positions. So we will have this total field at those sensor positions. Now, I represent this as a vector, which is this U evaluated at each discrete grid points in this sensor region. And this is the total field equals to the incident field. And then this is a matrix representation for this Green's function. And then this diag means I put this vector into the diagonal of a diagonal matrix, which essentially just means the point multiplication between F and U for this part, which is the discrete representation of this part. So this would be the field or the data that we collected at our sensor positions. But we noticed that in order to evaluate this field, we have to be able to know what is the total field in the computational domain. And to do that, we just plug in rho in my computational domain, and we again discretize this integral equation. But now our Green's function will be with both rho and the rho prime in the computational domain, right? And then this will be the equation where we can compute the total field within our computational domain. So these are the two equations that we will be using for doing the inversion, which is, we call that PDE, constraint optimization problem. So recall that our measurements are only the total field at the sensor locations, which we know that we can compute in this way if we know the correct permittivity contrast F. And that's why we want to minimize this cost. So this is our measurement, and this is supposed to get me the measurement if I know the correct F. So we want to minimize the difference between this and our measurement over all the possible permittivity distributions. And usually we add a regularization for F just because this problem is so ill-posed, because our measurements are so sparse and is only within a very limited angle. So there will be a lot of solutions if we don't add any regularization. Commonly used regularization would be, say, a total variation semi-norm, which will promote piecewise constant structure. And then, as I mentioned earlier, we need to have a constraint for our total field within the computational domain, which comes from the integral equation. So this is constraint optimization problem for solving this inverse problem. So even in our learning-based method that we'll be talking about in a minute, we still use this kind of structure to do the optimization. The only change would be now the total field that we synthesize, the total field at the sensor location that we synthesize is no longer computed in this physics, like purely based on the physics way. That will be then approximated by a neural network. So this part will be approximated by a neural network, but the whole optimization procedure, that how we estimate the permittivity distribution, is still going to be using a gradient-based method to solve this optimization problem. And if we are using the learning-based method, the automatic differentiation is going to be used to compute the gradient of this cost. But for model-based method, we can either just plug in the representation for U total from this equation back into my definition for the cost function C, and then we use the train rule to do the differentiation, or we can use the at-rate state method, which is more commonly used for PDE constraint optimization. We are not going to go into details for this, but if you are interested, there is a reference that you can refer to later on. Here, this looks like a implementation details for our method, but actually this is the key idea for the Fourier neural operator that we will be talking about in our learning-based method. Is like this. I'm writing the matrix representation for this. Recall that this matrix representation is to compute this integration, right? So in practice, we're not constructing this matrix because this matrix is going to be too large. We are actually doing this in the Fourier domain. And this is actually the essential idea for the Fourier neural operator. So we are going to talk about the Fourier transform anyways. So let's just discuss that right now. And later on, we will go through it very quickly. And this also shows that we choose the Fourier neural operator to be the network architecture for our problem, not because this Fourier neural operator is one of the most popular architectures in the literature, but because we noticed there's a lot of similarities between the Fourier neural operator and what the physics are and what our model-based approach has already been using. We noticed these similarities. That's why we choose the Fourier neural operator for our learning-based method. Okay, so the key idea is that we want to evaluate this integral in a more efficient way. And this is, we can do that in the Fourier domain if our this integral kernel function is a convolution or a mixed convolution and a correlation, meaning that it is convolution in one coordinate and it is the correlation in another coordinate. So it can be shown that if we consider the free space at the background, and then the Green's function for the free space is a pure convolution operator, but if we consider layered structure, usually the Green's function can be separated into a pure convolutional part and then a mixed convolution correlation part. And in both cases, we can use the discrete Fourier transform and the inverse discrete Fourier transform to evaluate this integration. And for simplicity, let's just talk about the pure convolutional case, which is exactly the case that is considered in the Fourier neural operator. So to make things even simpler, let's just consider a 1D integration, which in the discrete form, we will say this is a vector that represents the Green's function, and then this is a vector that represents the multiplication of our permittivity contrast and the total field. And then we want to compute the result of that integration, which is actually called the scattered field in the scattering problem. So to evaluate that in the Fourier domain, first, let's remind ourselves what is the discrete Fourier transform and the inverse discrete Fourier transform. So for a vector of length n, the Fourier transform is defined as this summation. I will use the tilde to represent the vectors that is being represented in the Fourier space. And then to do the inverse Fourier transform, we will use this formula. And now consider the circular convolution, which is slightly different from the linear convolution that we need to do. That's why I'm using Y, not V, that the notation that I used earlier. So suppose that we have two vectors of length n, and then we want to do the circular convolution between them, which in equation, it is written as this convolution. And this notation means modulo n. For example, 2 modulo 6 is going to be 2. Essentially, it means taking the residual of the division, right? So 6 divided by 6, and there is no residual, so it's 0. And if it's a -2, and because -2 is -1 times 6 plus 4, so that 4 becomes our residual. So this is how we define the circular convolution. And then we can show just by these 2 lines of equation that if we compute the Fourier transform of y, right? And by definition, it is like this. And then we plug in this expression for y here, and then we do some manipulation, and we can see that the Fourier transform of y at a certain frequency, spatial frequency k, is exactly the pointwise multiplication of the Fourier transform of h and the Fourier transform of g. So that means in order to compute the circular convolution of these 2 vectors, we can compute them in the Fourier domain by first computing the Fourier transform of g and the Fourier transform of h. And then we do the pointwise multiplication in the Fourier domain. And then we do an inverse Fourier transform of the, after doing the multiplication, that will give me back this y, which is the quantity that we want to compute. And we will see this again in the Fourier Neural Operator, because the Fourier Neural Operator is just to parameterize the Fourier transform of that convolution kernel with the neural network structure. So those are the parameters of the neural network structure. These are, and then the rest is, as I mentioned, this, our goal is actually to compute the linear convolution, but in our computer, it used the fast Fourier transform, which is actually an algorithm to compute a discrete Fourier transform. And as we saw earlier, this discrete Fourier transform only you can only do the convolution in Fourier domain if we are doing a circular convolution, meaning that the convolution that we will modulo the index by n, but what we really want to compute is not modulo by coordinate by n. And then we need to do some manipulation to represent this linear convolution into this circular convolution form. And then we can use whatever our computer provides us, the FFT, to do this convolution, to do this linear convolution. Details are not important. The procedure is usually we pad n zeros to h, and then instead of doing endpoint DFT, we do 2 the endpoint DFT and IDFT. And then once we have the y, then we just truncate, or we just extract the first endpoints, and this will be our solution for v. Because if you evaluate these inner products, you will see that the first endpoints of y is exactly the v, which is what we actually want. Okay, if you are lost for this part, that's totally fine. It's not important. The important part is that we will evaluate the integral in the Fourier domain by taking the Fourier transform of the integral kernel, the convolution kernel, and then the Fourier transform of the vector, and then we multiply them in the frequency domain, and then we will do the inverse Fourier transform to get y, because this is what the Fourier Neural Operator does. So this is the important part, and this is not important if you are lost. Okay, this is what we can get from this purely model-based approach. This is the ground truth, and then this is what we were able to reconstruct. I would say this is a decent reconstruction given how limited our measurements are. But in order to use this approach, first, this approach only applies to very strict layered background structure. And also we need to either know or estimate the background. And then computing the Green's function is definitely very, very computationally expensive. So it will be interesting to see whether we can use neural network to accelerate the whole process without too much degradation in performance. So here we come to our learning-based methods. So for this neural operator, it is a mapping between functions. So what we need to be clear is what is the function space that we are mapping between. Suppose we have a bounded open set in RD. In our case, it's actually R2 because we're considering a two-dimensional problem. And then this is a function space for the input function, which is the input for the neural operator, which it takes value in, say, R2, and then it maps to some to a RDA space. And then the output function will also take in value in R2 and then maps to a function that is in RDU. Also, so the neural operator is trying to approximate a operator that maps the input function space to the output function space. There is a quite general architecture that has been proposed in this paper, where first I lift my input function into a higher dimensional representation space using this mapping P. And then that will be my first layer. We call that V0. And then recursively, we will define the next layer to be, first we have a direct linear, or both are linear, but this is like a direct matrix vector multiplication components. And then this is the kernel integration components, which is represented in this way. We have a kernel function that could depend on the input function, or you can choose it not to depend on the input function. And then it is the kernel integration with respect to this vector that is coming from the previous layer. So these are the two main components, and then we will have a nonlinear layer to make the whole neural operator more expressive. And once we recursively define these multiple layers, at the end, like the last layer, we will use another projector to project this vector in the representation space, which is usually higher dimensional, back into our output function space. So this is the whole structure of the, like a very general structure for a neural operator. And then the Fourier neural operator is considering a specific case where the kernel integral operator is a convolution operator, meaning that this function of x, y only depends on the difference between x and the y. So this becomes a convolution. And as we mentioned earlier, this convolution can be computed in the Fourier space. And this is exactly what the Fourier neural operator is doing. So to compute this integration, first we do the Fourier transform for the kernel, and then we do the Fourier transform for the other function. And then we multiply them in the frequency domain, and then we do the inverse Fourier transform to put it back into our physical domain. And then, so instead of parameterize this integral kernel in the physical space, the Fourier neural operator parameterizes this integral kernel in the Fourier space. So this whole thing is parameterized as R. In the graph representation, so we have our input function, and then we lift it into a higher dimensional space. And then we go through multiple layers of this Fourier transform, and then this is a direct matrix multiplication. And then at the last layer, we will project the higher dimensional representation back into our physical or the output function space. So this is the original Fourier Neural Operator. And as you might have noticed, we have already seen quite a lot of similarities between our model-based approach, or more precisely, how the Liebman-Schwinger equation look like and how the Fourier Neural Operator is doing. So based on those observations, we made some modification for the Fourier Neural Operator. Actually, it's based on the Bond series approximation for the Liebman-Schwinger equation. First, we need to specify what our input function space is. And in our case, we have this permittivity map, and then the real and imaginary part of the incident field. So our output space is actually a three-dimensional space, because we have a permittivity value, we have a real part of the incident field value, and the imaginary part of the incident field value. So it's R3. And for our output function space, we have the real and the imaginary parts of the total field. So it is R2. And we call that Bond Fourier Neural Operator, Bond FNO, maps this input function space to this output function space. And then, so this is the iterative Bond approximation to the Liebman-Schwinger equation. So we will, if we just have one order of expansion, that is called the first Bond, which is actually very commonly used when the objects are weakly scattering, because that only take into consideration the first reflection, and there is no multiple scattering being represented in the first Bond approximation. But if we keep higher orders in the Bond series, we can represent more complicated scattering structure. So usually the higher the order, the better. But in terms of training neural networks, if we use more layers, although that might correspond to keeping higher order terms from the Bond series, it probably needs more data to train the neural network. So there's a trade-off between how many layers you should use based on how many training data that you have available to you. So we did some modification to the Fourier neural network structure. First, we noticed that in our iterative Bond approximation, we have a convolutional kernel, but this kernel is not directly acting on the previous layer, UT. We also need to multiply that with our permittivity contrast. That's why when we take the result from the previous layer, we multiply we also lift our permittivity map into the higher dimensional space, so that the dimension of these two vectors match each other. So we will multiply the previous layer output with our permittivity map. This is the first modification that we did. And then the second modification is that we will also add in this incident field without any operation. So we will only do operation. So this Fourier transform part is actually doing this convolution. And then there are two sets of linear and nonlinear layers just to try to make the network structure richer. But we're not doing that to our incident field, because we believe that the incident field should be directly added to the previous layer. So this is the second modification. And then the third modification is that because this kernel function is not changing in each order of the bone series, that's why we keep the weights, including this R and also this linear layers. All these parameters will be the same for all this Fourier neural operator layers. So in the original Fourier neural operator, these R for each layer are different. The W for each layer are different. But in our modification, we keep the parameters to be the same value for every layer, just because we believe that this kernel is not being changed for every layer. So these are the three modifications that we made based on this iterative bone approximation to the integral equation. And then, so this is the test. So more layers can be interpreted as keeping higher order terms in the bone approximation. So theoretically, it should be more accurate. And indeed, in our test, we plot out the testing error as a function of number of layers. And we see that error is actually going down, and it kind of quite converged around 10 layers. And here we compare our modification to the Fourier neural operator and the Fourier neural operator without our modification. We call that vanilla FNO. This dashed line, so this is the test error as a function of frequency indices. So this frequency, not to be confused with the spatial frequency in the Fourier neural operator. So this frequency means that the temporal frequency of the electric magnetic field. So so this is the testing error as a function of those temporal frequency values. And this dashed line represents the performance of the Fourier neural operator without our modification. But we notice that with the same number of layers, which is this green curve, we all use 5 layers, we get significantly lower test error with our 3 modifications to the Fourier neural operator structure. So this confirms that incorporating the information or the knowledge that we acquired from physics really help with the design of the neural network architecture. And also because we tie the parameters for all the layers, meaning that we keep the parameters for every layer to be the same. It is actually easier to train. So this gives quite a lot of benefit in just use a little bit knowledge from the physics. And to solve the inverse problem, so if you recall that I mentioned this problem is very ill-posed, so we have to use some regularizer in our optimization problem in order to get a meaningful reconstruction. This is not the center part of the talk, but I just want to mention that we did use a autoencoder and a decoder structure to put a stronger prior into our reconstruction. So instead of reconstructing the permittivity directly, we actually we will pre-train this autoencoder and decoder, and during the testing part, we will keep the encoder decoder non-changed, or at most fine-tune it, and the real parameter that is being reconstructed is the latent space parameters for the autoencoder and decoder. And once that is being reconstructed, we will use the decoder to obtain the permittivity distribution. And then this is some examples of the test result, which we will also see later on when we go to our notebook presentation. But we are not going to see the result as good as this one, just because we will only be using CPUs, and there are only very few number of iterations that we can run within a reasonable amount of time on CPU. But these are all generated by GPUs, so it is better. So this is the last row represents some set examples of the ground truth permittivity distribution, and then this row is the result that is obtained by using our learned Bond FNO as the forward operator and use that autoencoder decoder as a prior, together with the total variation regularization as a regularizer. And then we solved the optimization problem and obtained this result. So we can see that the layered structure are usually reconstructed pretty well. And then the objects, sometimes we are missing a object, but most of the time we were able to reasonably reconstruct those objects. Okay, I think this is the end of the slides presentation. And if you have any questions or comments or suggestions, we can discuss now. If not, we can go directly to the notebook demonstration.
Yes, there's a question somebody asked. Let me read it out loud. They said, "This is the old-fashioned perturbation theory. How many orders do you keep in the Lippmann-Schwinger equation? Is it a hyperparameter?"
You mean the learning-based approach, right? Because for the model-based approach, we're not doing the approximation. We are solving the Lippmann-Schwinger equation. We are not using the Bond approximation. So the question was about the it's like this one, like how many layers we are keeping in the structure. Is this the question?
Fayez, Abu, if you can elaborate a little bit more on your question, so she can answer. They said, yes, the Lippmann-Schwinger equation is iterative. How many iterations do you keep?
No, so let me make sure. Are you talking about this Lippmann-Schwinger equation? This one I'm not doing iterative. I'm actually solving this fixed point equation in our model-based approach. So up to some like inverting this thing, we're actually using the conjugate, what's that called? Conjugate gradient method to solve this inversion. So up to some computational inaccuracy in how we compute this inversion, we are actually not doing the iterative approximation as we did in our learning-based approach. So there is no approximation in that sense in our model-based approach. And in this learning-based approach, yes, it is a hyperparameter that we essentially just choose the number of layers based on our testing error, because we saw that about 10 layers, if we keep increasing the layers, it looks like, at least for our data set, right? When we are talking about neural networks, we have to say for this specific data set, we noticed that the testing error is no longer going down if we keep increasing the number of layers up to 10 layers. So these results I'm showing here, which are presented in our paper, is using 10 layers. And in the notebook, I'm actually reducing the layers to 5 to make it a little bit faster because we only have CPU available there. So I'm not sure if I'm answering your questions.
It looks like you answered the question. They added one more thing. They said, so do layers equal terms in Lippmann-Schwinger equation?
Well, I think they are, probably that's my bad. The Lippmann-Schwinger equation is not an iterative approximation to the integral equation. Lippmann-Schwinger equation is the integral equation, which is like this. There's no sense of layers. And then I think the students was asking about the iterative bone approximation to the Lippmann-Schwinger equation, right? I think it's the one I'm writing here. Yes, this is the so this is the approximation where we do have like different layers. I wouldn't say it is exactly, we are not exactly doing this iterative form using this neural network structure because we actually lift our function into a higher dimensional representation space. So first of all, these in this neural network is not exactly U. It's actually the U being lifted into a higher dimensional space. So yes, we can kind of interpret like more layers represents more higher order terms in the bond series, but it's not like a very rigorous one-to-one correspondence. It's not like that. It's just we have this network structure that we try to design the network structure that make it look like this iterative bond approximation. And yes, in the high level sense, one more layer will represent one more higher order terms that we keep in the bond series. So theoretically, you should be able to represent more complicated multiple scattering in the field. Yeah.
Yeah, they said that you answered their question. So good.
Are there more questions?
Yes, there's another question. What if there is scattering by some other particles located in different places, like maybe parallel above or below it?
Yes. So actually, if we consider a sensor at a certain position, right? So here, and then the field will decay as it goes away from the sensor, from the transmitter. So if I have things that is very far away from our sensor, and then the effects of those objects are usually pretty weak. And in that case, we will, at least compared to the object that being closer, the effects from those objects and further away is weak enough that we can kind of ignore that when we consider the measurements that are being collected within this region. Is that am I answering your question or you are asking something different?
Is it so it's like a decay function of amplitude?
Yeah, so when we compute the incident field, unless you are talking about the plane wave, but in practice we usually have those. At most, we will have the spherical wave, so it will decay as it goes away in distance. And most of in most practical cases, we actually have those antennas, which will make the field even more directional. So it is not a very weird assumption to assume that the objects that are located far away from the transmitter does not affect the received field too much in that case. Yeah. Yes, the amplitude of the incident field will decay if we consider it like a spherical wave.
Those are all the questions I see right now.
Okay. So shall we go to the notebook now?
Yes, let's do that.
Okay.
Good, thank you. That was absolutely fascinating.
Thank you. So the notebook, now I have the copied version open, and hopefully everybody else have the original copy downloaded and opened. Yeah, so we will start to look at the code. And I think the first few cells is what you have been doing for all the other modules. So first you set your name and the date, and then you want to mount to the Google Drive. And then for this, since now we are using this Google Colab, we only use CPU as our device. But if you have a GPU available on your local machine and you want to download everything onto your local machine, you can set it to be CUDA, and also you change some path, and that will be a lot faster. But for now, let's just use CPU for, let me see, maybe I should run it because it's a copy. Now want to mount it, and we need to give permission. Okay. And then we set the top level path to be our shared drive. And I think this is the same for every module. And then here we load the packages that we will need to use for our code. We mainly use PyTorch for our operator for our model, and also optimization. We use the PyTorch, and NumPy is used to mainly for plotting things. And then we do this, and here we are in module 3, inverse scattering application to ground penetrating radar. So we set the module path to be that, and our full module path will be concatenating the top level path with our module path, and this will be our full module path. And from there, we will be able to access our data and our pre-trained model. We are not going to train the model online just because the CPU will take forever to run. And also our pre-trained autoencoder decoder to represent the prior for our permittivity distribution. So this will be, everything is within this full module path. And here is the path that you need on your local My Drive or your own My Drive. And I think this is probably also the same for every module. And here, I have already created this folder and with the module 3 in there, which you can see maybe from here. If I go to My Drive, I have already created this folder, and I have created this module 3, and this was, you shouldn't be able to have this one at this point. I did this just before the talk, just make sure everything runs okay. So once you have that folders created, you can set your local save folder path to be that place, and later on, whatever plots or anything that you save will be saved to this folder. Okay, that's enough for setting the folder path. Okay, here is the main part of the code. First, we do some preparation, meaning defining some parameters. This part is the parameters for the neural operator. So modes means the spatial frequency, and maybe we'll go back to this a little bit. Let's go back to, yeah, if you look at this, the Fourier neural operator, right? So you take the Fourier transform and you ended up with quite a lot of spatial frequency components. Okay, in our application, I interpret that as a spatial frequency, just to be differentiated from the temporal frequency, right? But not necessarily for other applications of the Fourier neural operator. So I call it spatial frequency. So you take the Fourier transform and you ended up with quite a lot of frequency components. But in most cases, you actually don't need the higher frequency components. So the weights is actually only being multiplied to some lower frequency components. And how many frequency components you want to keep? It is a hyperparameter, but the paper of the Fourier neural operator suggested that usually keeping 12 is enough. So that's why we also keep 12. Okay, this is the modes parameter, meaning how many frequency components that you keep. And then this width is, if you recall that the Fourier neural operator will first lead the input function into a higher dimensional space. And what is the dimension of that higher dimensional space is defined by the width. We used 128. And then the number of layers is, yeah, how many Fourier layers that we want to use. And in our interpretation is what is the order of the bonds, the highest order of the bond series that you want to keep into the representation. So we use 5 in this demonstration. And the model type, I have included the definition of our modification of the Fourier neural operator. In that case, you will say bond will be that model. And if you say vanilla, that will be the original Fourier neural operator without our modification. And then for the pre-trained model, I think I have put in both pre-trained case for 5 layers and for both models. And then these are the parameters for the optimization that we used to learn the model parameters. So we used the Adam, which is a gradient-based algorithm. So we'll set the step size and learning rate and the number of epochs. And this is some kind of controlling the learning rate parameter. These are for optimization. And then here are for our specific data set. So in our data set, we have the incident field. We have so for each, we have 350 number of training samples and 50 testing samples. And for each sample, we have a permittivity distribution and the real and the imaginary part of the incident field that was going to be our input out of the neural operator. And then the output is going to be the total field. And each sample will have a different permittivity distribution. So we'll have a different output field. And then, so for the temporal frequency, so we solved the problem in the frequency domain. So if you pay attention to the details, so this is actually the raw data that we collected by the GPR is actually in time domain, but we do the Fourier transform for this time series, and we get the temporal frequency space domain. Okay. So we have 50 frequencies in total in our data set. And initially I thought that if I downsample the spatial space and the frequencies, the temporal frequency space, then we probably could train online with CPU, but it's not the case. So there is no need to downsample because for GPU, you don't need to downsample to make it run within reasonable time. And for CPU, no matter how much you downsample, it's not going to run within reasonable time. So let's not downsample. We just use the full data full resolution. So we have a 63 by 63 grid points for each sample. And here is if we are training the model online, then we need to create some folders to store some intermediate result, so that even if the code didn't finish or crash in the middle, we at least have something saved. But if we are not training it, there's no point to create these folders. And then so this is the folder where we have access to the pre-trained model. And then this is the path that we have access to the data. Okay, so these are the preparation, and these functions are just for plotting. And if we are writing the paper, that we probably want to fix the random seed, so so we can reproduce exactly the result that we present in the paper. But for the purpose of this demo, there is no need to set in this random seed. So let's just ignore that. Okay, so before we can train the parameters, we can learn the parameters, we need first to load the data. So here we have two functions. One is to normalize the data. So we just use whatever normalization method that is being used in the original Fourier Neural Operator paper. I don't understand why they do this normalization, but it looks like it really helps the stability of the training. If we do this normalization, is to subtract the mean from all the data set, and then normalize and then divide it by the standard deviation. So essentially, that's how they do the normalization. And then this function is to load the data that we saved in our data folder. We have three, which is we have three files. One is the free space, which is the incident field, and then this is the data frequency, meaning that this frequency just means it's a temporal frequency domain. And then this is the output field, which is the total field. So so this function is to load the data from that file. We will, after we are loading this, we will have this stored data input and stored data output. And then these are not very important, but these are going to be used for training. So the input data will have this epsilon, which is the permittivity distribution, and then the free space field, which is the incident field, because in this case we consider a free space background. So our incident field is just a free space incident field. And then for the output, it's going to be, we can load the total field or the scattered field, where the scattered field is simply the total field subtract the incident field. So it's the real and the imaginary part of the total field. This is going to be output from this function. And then we can define the batch size for the training. batch size, we use 64. For the testing batch size, we choose the number of frequencies. Just, it's not that important, but this is just to for easier plotting, to plot things in a more easier way. That's why we choose the batch size to be the number of frequencies, temporal frequencies. In our case, it's 50. Okay, so how we do that is we first apply this function to get this x, y, which is going to be the input and output of the neural operator. And then we will take the first n train number of samples as our training data. And then, so we kind of just say, because each sample contains 50 frequencies, so we kind of say each frequency will provide a distinct data. That's why we multiply by the number of frequencies. So although we have 350 training data set, and considering we have 50 frequencies for each sample, we actually have 350 times 50 number of training data points in our data set. And then the rest of them will be for testing. And then we do the normalization, which is subtract the mean and divide it by the standard deviation. This will be the input for the neural operator, and we do the same thing, the same normalization for the output. And then we use this function from the torch package to arrange it in a way such that we have each like in a batch size manner. So we'll have a train loader and a test loader. These are actually the structures that contains all the data for training and all the data for testing. In this case, I think I didn't. I think I should run through it so that it will take a while to load. Okay, now we're done. And then we can check. So we have 50 temporal frequencies and then 60 by 60, 63 by 63 spatial grid points. So that's the correct size. And then now we have our data loaded, we can define our model parameters, right? So this part is the original Fourier neural operator without our modification. We do need to change the function, the output function space dimension, but most of it just directly taken from the code from the author of the paper. This function spectral comp 2D, this is actually doing this thing. Let's see. Yeah, so that function is actually doing this convolution in the Fourier domain, this function. So if we can go to their definition of the function first, I take the Fourier transform using FFT. So they actually use real FFT. So assume that our input is real, then the spectrum is symmetric. So then this will will save some space for saving the Fourier domain data and also be faster. So we use this FFT, 2D FFT to first to do the FFT of the this is actually going to be the output from the previous layer. And then these weights are going to be the parameters. So these weights are that function R that are going to be learned. So after doing the FFT, we multiply the weights. And then after multiplying the weights, we do the IFFT. So this is the doing that, computing that convolution in the Fourier domain, right? So this is the main function for the Fourier neural operator. And this is the function that really defines the multiple layers of the Fourier neural operator that uses this function. I think the important part is here. Okay, so these are, for each layer, we will have this kernel convolution layer, which is defined by this function that we just talked about earlier, that computes the convolution in Fourier space. And this is the direct matrix multiplication layer, which is this part, right? So this is one part, and this is another part, and then we sum them up and use a nonlinear layer. And this is exactly what it's doing here. So for each layer, we will have a convolution layer and direct matrix multiplication layer. And when we define the function, so for every layer, we will have the kernel convolution part and direct matrix multiplication part. And then we sum them up, and then we use the nonlinear function. And then we will repeat for the number of layers. And after we get the output, we will project it back into the output function space. You can see the dimension for this FC1 and FC2. They actually first projected into an even higher dimensional space and then back into the output function space. So recall that in our case, our output functions are the real and the imaginary part of the total field. So it's two-dimensional. That's why, so this is the number of the output function space that we need to set for this specific case. And also for this lifting part, this is the input function space. So it will concatenate your function and then the grid points. So if your function is one-dimensional, then it's going to be 3. There's 1, 2, 3. But our function itself is 3-dimensional. That's why including this grid functions, the total input function is 5 in our case. So these are the two numbers that we need to set for the original Fourier neural operator to work for us. Okay, that's it. I think the structure is simple enough to understand. And then for our modification for the Fourier neural operator, this convolution function is almost the same. The only change is that now, instead of doing the FFT for the previous layer, in this case, which is X, I know the notation is weird, but this X here represents I would say the representation, the field in the representation space, right? So this is the field. So we want to multiply that with the permittivity map. This is corresponds to here, like, because our convolutional operator, we are doing the convolution of the Green's function and the multiplication of the sum function of the permittivity distribution and the output from the previous layer. That's why we added this multiplication here. So this is the only change that we need to make for this convolutional operator. And then for really defining the model, we will just have one convolutional operator, which is this convolutional operator. And recall that we have the same weights for every layer, so we don't need that sequential thing to happen here. We just need one convolution operator. And these are for the this linear, nonlinear, linear, nonlinear layer structures here. And these are the lifting functions or the projection functions that project from the representation space back into our output functional space, which is dimension 2. These are the same as the original Fourier Neural Operator, right? So, and then when we are defining each layer of the model, we will have a convolution layer, which recall that we multiply the permittivity distribution here. And then we will, here we will have that linear, nonlinear, linear, nonlinear of the output. And after that, we will add the incident field, which is this part. So we will lift our incident field to a higher dimensional space, and then without any operation, we directly add to this convolutional part. So this is essentially the code that defines our model. Okay. So once we have defined the model, this part is actually running the optimization to learn those model parameters, and we're not going to do here, just because we only have a CPU available. So if we say our model type is bone, then we will define our model to be defined by this function, right? And if we say it is vanilla, then it's going to be the original, the Fourier Neural Operator function that we defined earlier. So first we will define our model, and then we define our optimizer, which we use a variation of the Adam algorithm, which is a gradient-based algorithm. And then there is a learning rate scheduler, which is how you change your learning rate to promote convergence. And then, so the optimization is going to minimize some loss function. So here we define our loss function to be the normalized L2 norm between the total field from our data and then the total field generated by the neural operator. So this is going to be our loss function. And once we have that loss function, we will just looping over different samples, right? And then we will compute the objective function with the current estimate of the model parameters, which is, say, we will, for each training sample, we will evaluate our model using the current model parameters, and then we get the output. And then we want to, here is to define our cost from the current output from the model. And then this is going to be this objective function. And then use gradient-based approach, we first clean up the graph that computes the gradient, and then we do this backward, which will do the automatic differentiation to get the gradient. And then we will say step, and it's going to update our model parameter based on the gradient that we have computed. So this is the whole optimization procedure. The rest of it is just to save some intermediate result. And then, yeah, well, we're not doing here, but we do have some pre-trained model that is available in this folder. Save. in this folder. So these are pre-trained model that we can load, and you should load for evaluate the Fourier operator. And so this cell is really for you to run, and you can submit the result from, okay, let me say what you are going to get from this cell, and then I will tell you how to submit it if you are interested in evaluating this this model. So first we load the model from our pre-trained, we load the data from our pre-trained model. And then, so this path we have already defined earlier that will directly point you to the path where we saved our pre-trained model. And then we say, now we are evaluating the model. And here we can select a sample for testing. So we have 50 testing samples in our data set. So this number you can set to be arbitrary integer between 0 and 49. And then this file name is going to be, so you are going to generate a plot, something like this, and then you will save that plot as this image into your local My Drive folder that you have already created previously, like in the My Drive, and you created this and into module 3. So you will save that plot into your local folder, and then later on, so this is just essentially, I will evaluate the model from this pre-trained model parameters, right? And what the model output is the total field. And this plot just compares at different sensor locations, what is the total field from the data and what is the total field that is coming out, what that is the output from the learned model. So essentially these solid lines are the ground truth or from our data set. And oh no, so the dashed lines are the ground truth, and the solid lines are the output from our learned model. And you can see overall, it looks like it matches pretty nicely. And because we are only use 5 layers, it's not the best performance, but still it's pretty nice. So this is the plot that you will save. Maybe I should run it. Have I? I think it will like take about 20 seconds to evaluate that. So once you run this model, once you run this cell, let's see. Okay, and then you will have this picture, and with the name, you can change the name, but I'm just using this name, and then you will find it in your own My Drive in this folder in the module 3, and this is going to be that plot, and you can upload this plot to let me see, there is a README in this big folder in this shared drive, right? So if you open this README and then you go down to part 3, submitting results, and then if you click the link that says module 3, that is this current module, and then you click that link, you will be pointed to this form, and then you can upload the file here, and then you can submit. That is going to be the little exercise for you for this module. And actually that is all for our forward model part. And later on, we are going to talk about the inverse. But up to this point, do you have any questions about this forward model part?
Somebody asked, can we try changing layers or any other parameter to get different results?
Yeah, so you can change the number of layers, but then you have to train, because in the folder here, I have only provided you with the pre-trained model with 5 layers. And if you want to change the layers, yeah, you will get different result. And if you increase the layer, say up to 10, actually you can get the pre-trained model for 10 layers. If you go to the end of this notebook, I have a link to our the true code base for our paper. And I think there is a pre-trained model for 10 layers available on this web page. So if you are interested, you can also directly download that. But yes, if you have a GPU available, you can change this. You can change this layer number to a different number. Just don't make it too large, because it's probably will take too long to train, and because we only have a limited number of training samples. And if you do too many layers, also if you do too many layers, that could be overfit problems there, meaning that you will get very low testing error, but you will get very low training error, but then your testing error is going to be high if you use too many layers. So I would say maybe up to 15, maybe 10. I think 10 is a reasonable number that you can set. So if you have a GPU available, you can change that number, but then you have to you have to use a GPU. Otherwise, you will take forever to run on CPU. And then yes, you can change the layer. Yeah, if you change the device to GPU, the others will be the same, but it will actually run this cell. To prevent you from running this cell, I only allow you to run when you have a CPU, because this is the part that you use the gradient-based optimization to estimate the model parameters. And then once you have that learned, so your model will be saved in the similar naming convention, but with a different layer number, right? So my current layer number is 5, and say if you choose 7, then you will have a different name for the name of your model. And then when you load your model for evaluation, you need to load the model that you trained. So in that way, you can evaluate the result for different number of models, but then you have to spend the time for training. Okay.
Another
I hope
question
that is
is,
clear.
another question says, why are we using FFT twice on the function?
No, we use once and then we do IFFT, right? Let's see. Where is it? Define the model. Let's go back to the original. So this is FFT. And then we multiply the weights, and then we do IFFT, right? So this is to let's see. So we do this. We do the FFT of the function from the previous layer, and then we multiply the weights, which is to represent FFT of the kernel, but we don't parameterize the kernel in the physical space. We directly parameterize the Fourier transform of the kernel. So this is the FFT of the function. That is, let's say, that is this part of the code. And then we multiply the weights. That is this part, right? And then the whole result is going to be taken a inverse Fourier transform. That is this part. So this is IFFT. This is not FFT. The inverse Fourier transform. Is this the question? Is this the part?
There's a question, does the GPU model work on Collab or do we need to download it and run it on Jupyter? I think they're asking if the code is set up to use GPU here or if they need to change something in the notebook.
I'm not very familiar with the Google Colab because this is actually the first time I use it. I think you need to do some other settings to be able to use GPU on Google Colab. And I don't recommend you do that because I think they will shut you off if you use too many resources. So I would recommend that you download everything, including the data and the code, onto your local computer where there is a GPU installed, and then you run that on your local GPU. And in that case, you will not need to mount the driver. You will set this. You have your own freedom to choose however you want to name your folder and where you want to store your data and where you want to store your result, right? So all you need to change is the path for saving things or for loading things, and then you can directly just change this to CUDA. The rest of the code will run through if you do that. Just change the folder to whatever folder you prefer on your local computer, and then change this to CUDA. The code will run through. And if it is not, but I think it is, it's going to run because I tested before. It will run through. And if you have any problems, you can email me or you can go to our original code base from this web page. This is the same thing, but in a much more organized form. And it has the instruction to how to set the parameters and how to run it and how to create a CUDA Conda environment to run everything. Yeah, but I think this should run through if you just download everything onto your local computer and change the device to CUDA. Yes.
Somebody asked what they need to upload to the Google form. It says, do we need to upload the PNG file?
Yeah. Yeah, just please upload that file. If you have the resources to train the model for different number of layers, I'm happy to see that. Maybe you can upload later on, but if you don't, you can just, let's see where it is. Yeah, you can just select a testing sample that you want to test. It can be from 0 to 94, and then you will get this PNG file, which is this plot. And then you can upload this plot to the Google form. Yes.
Okay, those are all the questions I see right now. I think you're good to go.
Okay. Okay, let's do the inverse. So initially, I would wanted you to upload a picture of the result of the inverse problem. I think that would be more fun. But the CPU is really a big limitation. Like it limits how many number of iterations that we can run and limits how many number of temporal frequency components that we can use. So the result does not look very good. So I don't want you to upload a ugly result. That's why I'm only asking you to upload the evaluation of the Fourier operator, but I think the inverse part is more fun. So for the inverse part, first as I mentioned earlier, we will use some regularizers, and this is the total variation regularizer, which is essentially the sum of the L2 norm of the discrete difference in 2 dimensions. This is a commonly used regularizer for promoting piecewise constant of your reconstruction, which is the case in our scenario. So we will define the total variation loss, and then the whole inversion loss is going to be the total variation loss plus, we call that the data fidelity term, is essentially the predicted field from our Fourier model, which in this case is the output of the Fourier neural operator. And this mask I'm going to talk about later. And this is going to be the measurements which we got from the data. So we call this the data fidelity term, which is to penalize the difference in the total field. And then we will add the total variation. So this is a whole inversion cost. And then here, okay, I think I should run while I'm talking about it. So here is, again, we are loading a pre-trained forward model. And in this case, we are loading the same model that we have used before for our forward model evaluation. So we will load the model and say it is evaluation. And then this prior that I didn't spend much time to talk about because I don't think it's very important. It's this autoencoder decoder part to better parameterize our permittivity distribution. So we just we will optimize over the latent space parameters, and we limit our permittivity to be in the range of our auto decoder. So this will act as a pretty strong prior to regularize this highly opposed problem. So you don't need to think too much about it. You just load it, and I have already put it in here, has already been pre-trained in this prior folder. So you will load this file that will give you the autoencoder decoder structure as a prior. And then, so this is the mask that you see in our definition for the inverse objective function, right? So we multiply the predicted field with the mask. So the output of our Fourier neural operator of our forward model is the total field at every grid points, right? Let's go to another. Maybe this is a picture to see. So this is a better picture to see. Okay, so the output of the operator is going to be the field at every grid points, which in our data set is 63 by 63. But for our measurements, right? So we are doing non-destructive GPR, right? The ground penetrating radar. So our measurements is only like some line in the air. So the sensor location is actually only in this case. So we are only allowed to use the data collected at these locations for the inversion. That's why we have this mask. So everywhere else is 0, and only this one row is 1. So we will pick out the field at these points from both the output of the neural operator and also like the output field from our data set, because that is considered to be the measurements that is available for inversion. If we have access to every point from the total field, then the inversion problem is going to be a lot easier, but that's not the case in the ground penetrating radar setup. We only have access to the field that we have collected where our device is in the air, right? So this is one row. So this is what that mask is doing. And then this function just defines the whole optimization procedure for using optimization approach to solve the inverse problem. So this is the details are not so important, like how we don't use all the temporal frequencies at once. So we will start from the lower temporal frequency and gradually adding higher temporal frequency, just because when the temporal frequency gets higher, it is already a non-linear a non-convex optimization problem, and the landscape of the objective function is even worse at higher frequency. So we kind of want to drive our solution into a reasonable local region with lower frequency components, and then we will start to add higher frequency measurements to refine our reconstruction. This is not so important, but actually once we have defined our objective function, we again will define our optimizer. We again use this Adam optimizer that is the same gradient-based algorithm that we use for training the neural operator, but it is just an optimization algorithm. So if you have an optimization problem, then you can use it to solve. So this is again the same gradient-based optimization, and we will these are not important as well. Let's see, decode. So this is the latent space parameter, and once we do the prior decode, this is giving us the estimated permittivity distribution. And then the estimated permittivity distribution is going to be concatenated with our incident field, which is in this procedure. You can ignore the filter. This is just some tricks to make the performance better, but it's not essential. So this is the parameter that is being estimated, the latent space parameter. And we use the autoencoder decoder, the decoder part. After decoding, we will get into our permittivity distribution space. So this is the estimated permittivity. And then we concatenate the estimated permittivity with our incident field. This is going to be the input for our learned model, right? So we put that into the model and we evaluate the model. This is going to give us the total field at every grade point. And then this mask is going to be masking out everywhere else except the row where the sensor is located. And then this is our loss. And then once we have that loss, we will clear up the graph for computing the gradient. And now we compute the gradient. And then the rest is just for, and then we do the step, of course. And then it's, yeah, and the rest are just saving things and the plotting things and printing things. It's not very essential. It's just, yeah, I think the recap to make things simple, we just need to define the objective function. Actually, you can change it. Say you can change it to other. We use the L2 norm squared. You can actually define other maybe metrics, whatever you want, but you want it to be differentiable. And then once you define the objective function, then you choose you load your model, and then you choose the optimizer. We use Adam, and then you can, because the gradient now is computed using automatic differentiation, you don't need to worry about how you compute the gradient. So all things becomes quite easy. So once that function is defined, here again, you can choose a sample to evaluate, and similar to the case where you evaluate the Ford model. This sample can be from any integer from 0 to 49. And once you selected a sample, I have two setups. So this is the ideal setup if you have a GPU. So you will use all the temporal frequency components, and you will run more than 1,000 iterations. And then you use that filter trick to make the performance a little bit better. But if you don't have a GPU, if you use CPU, and that will downsample the frequency by 5. So we have 50 temporal frequencies in total. If you downsample by 5, we are only using 10 frequencies for reconstruction, and we are only running it for 100 iterations. Even with this, it is still very slow, and it takes about 8 minutes to finish the whole process. I think we can, let me see, I run this cell. Yeah, so after this setting, we will call this function to get the estimate, and this will take about 8 minutes. And maybe we shouldn't wait for 8 minutes. I will just let you know what is going to happen after that. So that function will give you the estimated permittivity distribution at every maybe every 5 iteration. And then you want to take the final result. Oh, this part is just to see how the algorithm converge. So this is the objective function value. Ideally, you will see it is decaying. It can decay further if you allow more iterations, right? And then this is the MSE for the latent space parameter, and this is the MSE for the permittivity distribution, meaning it is you input the latent space parameter, the estimated input latent space parameter into the decoder, and you will get the permittivity map, and then you can compute the mean. MSE stands for mean squared error for the permittivity distribution. And then we can see how. So once we have this estimated permittivity distribution, so this is like, as I mentioned, we have saved the permittivity distribution every 5 iterations. And when we take it from the final iteration, is our final estimation of the permittivity distribution. And then we can concatenate that with the incident field. And then this is our estimated input to the model, right? Then we can evaluate the estimated total field at the sensor locations, and we can plot out how close they are to our data. Surprisingly, you will see, once the result is out, you will see that the permittivity distribution with only 100 iterations is actually pretty bad. Surprisingly, you will see that it actually has already matched the data pretty well, because let me see, I think I can show you what you will get. Oh, not this one. Okay, I don't think I saved it. Anyways, just let's wait a little bit. You will see that actually the layered structure has already been reconstructed pretty well. It's just the objects are messy. What I mean by the layered structure is, so we have this layered structure, and then we have these objects. And you will see from this evaluation with only 100 iterations, you will see actually the layered structure has already been reconstructed in a pretty accurate manner. And actually the total field is dominated by this layered structure. That's why, although the objects are not estimated correctly, the total field at the sensor has already matched the data pretty well. And that's one of the reasons why we actually need a very strong prior to regularize the problem. Otherwise, like any reconstruction of the objects will give you a total field that are quite similar to the true data. So, so actually, when we run more iterations, I think this is an important part I need to mention. like after some iterations, I think we set it to be 300 in this case. So after 300 iterations, we will start to fine tune the autoencoder decoder parameters for our prior. So that means after 300 iterations, for the first 300 iterations, we keep the parameters for this autoencoder decoder to be the same, unchanged, just use the pre-trained value. And after 300 iterations, we jointly estimate the latent variable and the model parameters just to fine tune the prior. So that really helps to get the better reconstruction of the objects. But for CPU, we're not doing that because it's just too slow. This is already slow enough. It's already 70%, so hopefully we'll get the result very soon. While we are waiting for it, are there any questions about the inversion part?
I don't see any questions yet. I'll wait a minute.
Okay. So again, if you have a GPU available, you can try use a better setting and use GPU. Even with this many number of iterations and with all the temporal frequency components, it will take like 1 minute to do this inversion on GPU. Well, it depends on your GPU. So I have a pretty good GPU. So maybe if you have a less good GPU, it might take a couple of minutes, but it's not as long as it is on CPU. So yeah, so if you have a GPU and you want to try it, please feel free to also upload a reconstruction result that you will see here. Okay. Yeah, so this is the result. Oh, we only use 10 frequencies. That's why both cases. I think this is like the after 1 iteration, I think you get this, and then after 100 iterations, and this is what you get. You can see that after 100 iterations, the layered structure is actually reconstructed pretty nicely, and the messy part is just these objects. It just have trouble figuring out how the objects are. But if you look at the error map, the layered part is actually at least the first layer is getting the correct layer, and then the intersection of the layer is kind of correct. But if you let it run more iterations, you can expect something like this. The objects are almost there, and then the layer is even better. I think here is not plotting the first layer. That's why you only see 2 layers here. But like this is air, where we assume we know where the first interaction is, the first interfaces. So it's not showing in this result, but you will see even for the deeper layer that has not been reconstructed well in this case, but if you allow it to run more iterations, you will be able to get the deeper layer more accurately, and also the objects will be there if you run more iterations. Yeah. Okay, I think that's all I have for my notebook. So if you have questions, comments, suggestions, we can discuss now. And if you have other questions from the previous presentation, please feel free to ask as well.
Thank you. That was a very good presentation. People are going to need to ask through the Q&A.
Oh, there is the Q&A.
Yeah, there's a Q&A window.
Oh, okay. How do I go there? It's not here?
So at the bottom of your Zoom window, one of the icons, I think it's the fifth one along, says Q&A.
Let me stop sharing for now, maybe.
Yes, sorry, that's right. You're
Okay, I'm a little bit confused. Where's the Q&A?
Zoom window.
Oh, yeah, I saw that. Should I click that?
Yes, please do. And the first top thing is it says open questions. Lazar has been very kindly answering many of them, but there are two. You should be able to see two open questions.
Yes. Click on the arrow beside RAM disk option, then select. Oh, I think that's a comment that how you use GPU on Google Colab, right? Yeah, I think those are the comments about like what is the GPU availability on Google Colab, and then yeah, I don't think those are questions. Those are more about like comments, like whether you can use how you can use GPU on Google Colab and what is the computation time limit. Yeah.
The 100 frequency version that's taking nearly 4 hours is.
I'm sorry.
Is it the 100 frequency bin version that takes nearly 4 hours? Their comment GPU gives a runtime of 3 hours 40 minutes. Do you think that's the version for the inversion? Is that the version with the inverting?
Yeah. So the inversion part only take one. Well, I don't know how the GPU on Google Colab compared to the GPU on my own desktop, but on my own desktop, the inversion for one sample only take 1 minute on GPU.
I see.
Yeah, but I think the 4 hours is not enough for training the model. Yeah, I think for training the model, you probably need to download everything onto your local drive, onto your local computer, and then to train it. But if you just want to do the inversion part, yes, you can load our pre-trained model and you use the Google Colab GPU. I think it's probably not going to be 1 minute, but I would say a couple of minutes with the full setting, like with all the temporal frequency components and with more than 1,000 iterations, maybe a couple of minutes is a reasonable estimate for that time. Yes.
There's another question concerning other applications of the Fourier FNO and
yeah, so this inverse scattering, I'm more thinking about from our from MERL, right? Actually, in medical imaging, there are a lot of inverse scattering problems. But in that case, actually, you have a tissue of the body of some animals, but then you have measurements everywhere around that tissue, and then that tissue is actually in free space. So in that case, I don't think a neural network is, at least for the forward model part, you can use neural network to get a better prior for the problem. But I think for the forward model part, because everything, if it is embedded into free space or a homogeneous medium, because in that case, the Green's function is easy to compute, and the whole thing is very well modeled just by pure physics. I don't think you need the neural network to learn the forward model. but you can if you want, because there are still benefit is in that case, the gradient is computed using automatic differentiation, and then you don't need to do that adjoint state method. If you are too lazy to derive it, or if you are too lazy to code it, then you can, yes, you can still use a neural network and you can use the automatic differentiation. I think that is the part that you can save some work. But I think this is more like using a neural network to model the fourth model of the scattering problem. I think is more useful when you have the unbounded, when the unknown permittivity is unbounded. And in that case, how to cheat the artificial boundary that when we limit our computational domain to be a bounded space, I think that is where it is useful. And I think this ground penetrating radar is the application that I have in mind for now. But I would say whenever you have a unbounded background, unbounded and unknown background, and then you don't know how to deal with the boundary condition efficiently, and in that case, I think maybe use a neural network to train is a effective way to do the modeling. Yeah.
I see another question. It says, would it ever make sense to allow FNO layers to have varying weights that are also optimized for?
Yes, that will be. So in the original FNO layers, they do have different structure. They do have different weights for different layers. But we have tested out that if we keep the weights to be the same, the performance is better. And you can also see from oh, am I not sharing now? If I'm sharing now, can they still see my screen?
We can't see your screen yet.
Oh, they cannot see my screen. If
No,
I'm not sharing right now, if I'm sharing.
Oh, you should be.
Okay. Wait, I don't think I can share now. The problem is, okay, there we go.
Green.
Yeah.
Yeah.
Okay. Yeah, I guess now they can see my screen. Yeah, so this dashed line is the original Fourier Neural Operator, which does not keep the weights for all the layers to be the same. They have different weights for different layers. And then this green line is the same number of layers. So this is 5 layers of FNO with different parameters for different layers. And then this green line is 5 layers of our modification of the FNO. Of course, other than tying the weights, we also did some little other modifications, but I would say the performance gain is mainly from tying the weights. Yeah, so you can see the performance is actually better. You are getting lower testing error if we keep the weights to be the same. Yeah.
I think we very good. You've done a very good job of clearing all the Q&A. Now, a combination of you and Lazar, we've actually got to the point where that's all the questions. So I think we can draw to a close then, and enormously appreciate Yanting. That was
Yeah.
Number of questions I've had for actually, gosh, probably 2 years now. Concerning this type of guessing and optimize Green's functions related problem. We'd actually talked about it. I honestly hadn't quite appreciated how long it would have taken us to come up with this without your guidance. So this is enormously valuable.
Yeah, thank you, Lazar, for typing all the things. I didn't realize that I need to type until I saw that it shows that Lazar is typing. I was like, oh, am I supposed to type it?
Oh, no worries. Just wanted you to
yeah, thank you so much. Like, I have no idea that I need to do that.
Sorry, will be copies of all the questions and the answers copied into the the directory you have access to. So in case you want to review any of the inputs. But,
Okay.
yeah, I think we're going to wrap up at this point.
Yeah.
So we start again tomorrow, 10 a.m. US Eastern time. Please go to the Indico. You should be able to access the the directories already, so you can see the material that is going to be covered. But thank you very much, everybody. Really appreciate your participation, and the form input. You can get the link if you still want. If you need the link and you've lost the other material, you can go to the README file to get the link as well for submission. If you can, I know our previous presenter said, you can submit all the way to the end of the week, but we actually, for each module, we'd like to be able to see, within a couple of hours at the end of the module, what people are submitting. So, but please do, if you can, finish off the piece of work, and give Yanting the upload. Thank you. Okay, we're going to stop.